right, today we're going to cover our last section in the chapter, section 8.7, titled Probability. And I hope you're a little bit familiar with probability. It's probably not the first time you've heard this in high school. Probability is essentially the chance that something is going to happen. And for our definition, probability is essentially a fraction. All right, so in terms of the top of that fraction is you're going to figure out the probability of something. There's obviously a desired outcome and a number of total outcomes. Some of them which you want and some of them which you don't want. So the way you're going to figure that out is you're going to take the number of successful outcomes or desired outcomes, and you are going to divide them by the total number of outcomes. So you can never have the top be more than the bottom, because every successful outcome, you're obviously going to have more total outcomes, or at least equal. So that lies the difficult part about probability. Probability is a lot of counting. It's counting how many successful outcomes are there over how many total outcomes are there. And when I say counting, I'm referring back to our last section, the principles of counting, where we learned about permutations and combinations. And that's what makes this lesson difficult to teach, because there's so many different types of problems, so many different ways to count, that it makes it tricky to show. There's a lot of different types of problems. You have to be able to, if you're struggling in 8.7, it's usually go back and review 8.6, and it helps. All right, so a probability of 1. All right, what does a probability of 1 mean, as opposed to a probability of 0? Well, if probability is always between 0 and 1, 1 means it is certain. It is going to happen 100% of the time. There is no chance it won't happen. And a probability of 0, that means there is no chance, not even 1 in a million. All right, there is no chance of that happening. A probability of 0.5, that's what we refer to as usually like 50-50, right? Like flipping a coin has a probability of 0.5, taking a dice, rolling an odd number has a probability of 0.5, picking a red card out of a deck of cards has a probability of 0.5. Okay, so let's start talking about total outcomes, all right? And then we'll move towards taking this to probability. How many total outcomes are there if you toss 2 coins? So this goes back to our fundamental principle of counting. You're going to flip the first coin, there are 2 possible outcomes. You're going to flip the second coin, there are 2 possible outcomes. Fundamental principle of counting says we can multiply those and get 4 total outcomes. Now, on an easy problem like this, it might be worth listing the 4 total outcomes. You could actually list them out. Now, if we flipped 10 coins, I wouldn't want you to list out all the possibilities, because there'd be way too many to list. All right, how many total outcomes are there if you toss 3 coins? Well, it uses the same fundamental principle of counting, except here you're flipping 3 coins. There's 2 outcomes when you first flip the first coin. There's 2 outcomes when you flip the second coin. And there are yet again 2 outcomes when you flip the third coin. Fundamental principle of counting says we just multiply. And if we wanted to list all of those out, we could do it, although it's, let's see, all heads, 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 tails, heads, tails, heads, tails, heads, heads. We could go tails, tails, heads, tails, heads, tails, heads, tails, 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 tails. Could list them all out. Now again, as it gets much further, you're going to find the possibilities, the number of outcomes increase pretty rapidly. If 2 coins are tossed, what are the probability that both land tails? So this goes back to the last question. If 2 coins are tossed, I'm looking for the successful outcomes, or we can call it the desired outcomes. Successful outcomes over total outcomes. All right, well, on the previous slide, we already figured out there are 4 total outcomes. How many of those 4 outcomes land tails, tails? Well, if you have 2 coins, there's only one way to land tails, tails. If the first is tails and the second is tails, the probability would be 1 out of 4. If a card is drawn from a deck of cards, so a standard 52 cards in a deck, What is the probability that it is an ace? For this section, it is worthwhile that you know a little bit about a deck of cards, like there are 4 suits, 26 of the cards are red, 26 are black. There are 4 of every number. If you think of aces as ones, all the way up to 10, there are also jacks, queens, and kings. If you know all that, then you're probably good in terms of probability. What is the probability it is an ace? So I just said aces are like ones, and there are 4 of them in the deck. So if I think successful outcomes over total outcomes, well, if there's 52 cards in the deck, then I'm picking out of 52 possible outcomes. 52 possible choices I could pick, I'm going to pick at random. There are only 4 in the deck that are aces, and I would reduce this to 1 over 13. Divide the top and bottom by 4. That gets me to 1 over 13, which would be the correct probability. And leaving it as a fraction is preferred. If you gave me a decimal, you'd have to round. So, all right, so let's update it a little bit more, up the ante a little bit in terms of probability. 2 dice are rolled. What is the probability that the total is 7? So this is like playing Monopoly. You throw 2 dice, and you want to see what they add up to. So let's first think. I always like to look at total outcomes first. And if I'm going to roll 2 dice, that's 2 events. The first dice has 6 outcomes. The second dice has 6 outcomes. So you should be saying to yourself, there are 36 total outcomes when you roll 2 dice. All right. Now the question is, how many of the total outcomes add to 7? Which is essentially like asking myself, how many different ways could I use the numbers 1 through 6 to add to 7? All right. And I could think I could get a 1 and a 6. That would be 7. I could get a 2 and a 5. I could get a 3 and a 4. And then when I'm really looking, this first column here is my first dice. This is my second dice. So yes, 4-3 is a different outcome because it's on different dice. 5-2 is a different outcome. 6-1 is a different outcome. Total, there are 6 different outcomes that add to 7. I can't use 7 and 0 because both 7 and 0 are not on dice. So 6 over 36 would be my total number of ways to roll to 7 over the total number of ways to roll 2 dice. That reduces down, divide both top and bottom, and you get your answer 1/6. All right, so here's a big question in terms of using the counting principles. Permutations versus combinations, and which one do I use? So the lotto, this is an older question. The lotto uses more numbers now, but let's say that the lotto uses 38 numbers, and they select 6 in any order. If you buy 1 ticket, what are your chances of winning? And the hardest part to this problem is students don't know, should I use a permutation or a combination? So if you think about what permutations do, permutations take into account how many different ways can you order 6 numbers out of 38. So the idea there, 1, 2, 3, 4, 5, 6 is different than 6, 5, 4, 3, 2, 1. Right? Those are 6 numbers, 1 through 38, and I just picked the easiest 6 to work with. But permutations count these 2 as different. But in the lotto, your order really doesn't matter. You want how many different combinations, because a combination is going to find how many different ways can you group 38. How many different ways can you group 6 numbers out of 38? So what we are doing here is we're doing 38 choose 6, right? 38 choose 6, and again, we're trying to group those. So the calculation for that is 38 factorial over 6 factorial. No, over 38 minus 6 factorial. So what that really breaks down to is 38 times 37 times 36 times 35 times 34 times 33. I seem to have left out right here the 6 factorial by accident. So there's actually two factorials in the bottom of that. It's 6 factorial and 32 factorial. So what we're left with is essentially the 38 factorial and the 32 factorial from this piece. This would be 32 factorial. Those do a lot of canceling out, and then we're left with 6 times 5 times 4 times 3 times 2 times 1. And you put that into a calculator, simplify as you need to. What that comes out to is 2,760,681. All right, so those are 2,760,681. That's the number of different winning combinations for the lotto. Well, you're buying one ticket. Well, that's one way of winning because you have one ticket out of 2,760,681. So you usually see a lotto like this in the smaller states where there's not that many people buying tickets. As you get to bigger states, they have to increase bigger numbers. That's why if you notice Powerball has so many numbers. Because it's nationwide, or a lot of states, not many. Okay, a probability concept called mutually exclusive. Two events that do not have any successful outcomes in common. All right. Going back to a problem we looked at before, to find the probability of two mutually exclusive events, like rolling two dice and getting a total of 6 or 10. All right. You do it by adding their probabilities. So we already did a dice problem, and when you roll two dice, there are 36 total outcomes. Now, what I want is the probability of getting a 6 and the probability of rolling to 10. So the question is, how many different ways can I roll to 10? Oh, I'm sorry, how many different ways can I roll to 6? I could do 1 and 5. I could do 2 and 4, 3 and 3. No, I can't list 3 and 3 again because that would be exactly the same outcome on my first dice and second dice. But I can list 4, 2 because that's different. If you notice, the first and second dice are different. So that is 5 different ways to roll to 6. And if I want to say how many different ways can I add to 10, well, that's going to be 4 and 6, 5 and 5, and 6 and 4. So 3 ways. So total, the probability of both, when we add these fractions, they already have common denominator, so it's pretty straightforward to add. 8 over 36 reduces to 4 over 18, which is the same as 2 ninths. 2 ninths would be your probability of rolling a 6 or a 10. And those two events are mutually exclusive. There are no successful outcomes in common. There's no way to roll a 6 and a 10 at the same time. All right? But sometimes events share successful outcomes. All right? So think of a deck of cards. If I ask what's the probability of picking a heart or a face card, we are still adding their successful outcomes. So we already talked about cards. So I know there are 52 cards in a deck. If I want to know the probability of picking a heart, right, I know there are 13 cards in a deck. Right? And the probability of picking a face card, there are jacks, queens, and kings, so there are 4 of each. That's 12 cards in a deck of cards. People would think there are 25 out of 52 ways to do this, but that's not true. Some of these pieces have been double counted. There are 3 cards that are both hearts and face cards. There's ones that we counted in both, and they've essentially been double counted. Those 3 cards would be the Jack of Hearts, the Queen of Hearts, and the King of Hearts. So the last piece to this is we need to subtract out the events that are in common. All right, what numbers were in both sets? So if you can still add, but you do need to subtract out what's in common. What's a heart and a face card? What makes both true? Because we've double counted them. Which leads me to an answer here of 22 over 52 reduces down to 11 over 26. All right, so this is a good place to stop. We will finish the rest of this lesson in class. We are going to bring your books to class. We'll look at an example. There's a nice chart on page 617, example 8. We'll look at that the next time I see you.